Hi, I'm Matt Samuel, and welcome to my video about a Pieri formula for multiplying double Schubert polynomials by factorial Schur polynomials corresponding to partitions of row and hook shape. So I'll start by defining the symmetric group S infinity. It is the group of all permutations of the positive integers, fixing all but finitely many elements. So a special element of the symmetric group Si is the adjacent transposition, which exchanges I and I plus 1. Tij is the transposition exchanging I and j. And Sn is the subgroup of all W in S infinity, such that Wi is equal to I for all I greater than n. And an important statistic of a permutation is the length, Lw, of the permutation W, and it's the number of inversions as a permutation. So double Schubert polynomials represent Schubert classes in the torus equivariant cohomology of the complete flag variety of type A. They are polynomials in two infinite sets of variables, x and y, which we abbreviate as x and y, but they are index variables, xi, I and n, and yi, I and n. And these double Schubert polynomials form a basis for the polynomial ring Zxy as a module over Zy. They are indexed by the symmetric group S infinity, and we write them with an S in a funny font, Su, x and y for u and S infinity. And you can see a more detailed introduction in my Schubert seminar video. So I'm going to talk about divided difference operators. There is an action of S infinity on the polynomial ring obtained by permuting the indices of the x variables. So if we define, well, we've already defined Si to be the adjacent transposition. We can define a divided difference operator in terms of this adjacent transposition. It's 1 over xi minus xi plus 1 times, and then in parentheses 1 minus si. So if we apply this to a polynomial, you take the polynomial, subtract what you get when you exchange an xi and xi plus 1, and you divide by the difference xi minus xi plus 1. So these act very nicely on the double Schubert polynomials. We'll see why in a moment. So if you apply partial si to su of x and y, and the length of usi is less than the length of u, then you get susi of x and y. But if the length is greater, then you get 0. So the divided difference operators can be multiplied as operators, and they combine to form composite divided difference operators partial u, again indexed by u and S infinity, and the relations are similar if you're familiar to the symmetric group, except that the divided difference operator squared is 0, corresponding to adjacent transpositions at least. So double Schubert polynomials can be defined in terms of divided difference operators. So we take a specific permutation W0 of n, and this is the longest element of Sn plus 1, which is the reversal permutation, and we define a double Schubert polynomial SW0n of x and y to be the product as I plus j ranges from 2 to n plus 1 of xi minus yj. So then for u and S infinity, to define the general double Schubert polynomial, we apply partial u inverse W0 of n to SW0n of x and y, and this should make it pretty clear why the divided difference operators act so nicely on the double Schubert polynomials. They're used in their definition. So I'm going to talk about the structure constants of double Schubert polynomials. Since they form a basis, they're structure constants CUVW of y that are polynomials in y, defined by taking the product SU of xy times SV of xy and expanding in terms of the basis, and the coefficient of SW of x and y is CUVW of y. So this is known to be a polynomial in the differences yi plus 1 minus yi with non-negative integer coefficients, which was proved by Graham in 2001. So I'll refer to this as Graham positivity. No positive formula is currently known, although some partial results are known. So we're going to generalize these structure constants to introduce what I call the Molev-Sagan problem. We take a third infinite set of variables z and consider the product su of xy times sv of xz and expand this in terms of the basis. And the coefficient of sw of x and y is cuvw of yz. Now this will be our object of study. So I have a conjecture that the coefficients cuvw of yz are polynomials and the difference is yi minus cj with non-negative integer coefficients. This is pretty hard to test. I've tested it up to n equals 5, and I'm using Kellen-Meyer's machine to test n equals 6, and it's been running for months, but the end is in sight. Although it may not be necessary to test once it can be proved with algebraic geometry, although that has not been done yet. So I'll mention the skew-divided difference operators in the Leibniz formula. So the divided difference operators satisfy a product rule, also known as the Leibniz formula. If you apply partial w to the product pq, you can expand this as a sum over all u and s infinity of partial u applied to p times this new operator partial uw applied to q. So these are the skew-divided difference operators partial uw, and this can be seen as the definition of those skew-divided difference operators. So the importance of the skew-divided difference operators is if you take any polynomial p and a permutation u and s infinity, you can multiply p times su of xy and expand this in terms of the basis, and the coefficient of sw of x and y is the skew-divided difference operator partial uw applied to p, substituting y for x. So in particular, the Molev-Sagan coefficient cuvw of x and y is the skew-divided difference operator partial uw applied to sv of x and y. So now we'll move on to Pieri formulas. In 1996, Sottile presented Pieri formulas multiplying an arbitrary ordinary Schubert polynomial, not a double Schubert polynomial, by either an elementary symmetric polynomial or a complete homogeneous symmetric polynomial, as well as by a Schur polynomial corresponding to a partition of Hooke shape. So in the paper, a Molev-Sagan type formula for double Schubert polynomials, I provide a Pieri formula for multiplying a double Schubert polynomial by a factorial elementary symmetric polynomial in a different set of variables. So in this talk, I will complete Sottile's cases of Pieri formulas. I'll present a formula for the Molev-Sagan case for factorial complete symmetric polynomials and factorial Schur polynomials corresponding to partitions of Hooke shape. So I'm going to define Young tableau. These are very common in the field. Although they're not often used for double Schubert polynomials, it's more of a Schur polynomial thing. So let lambda be a partition, which is a non-increasing sequence of positive integers. And let k greater than 0 be an integer. And a semi-standard Young tableau on lambda is a filling of the Young diagram of lambda with positive integers that strictly increase along the columns and weakly increase along the rows. So I'm going to write this as a function from the Young diagram expressed as a set of boxes to positive integers, with the entry of a box b being t of b, so where t is the function. So an example semi-standard Young tableau for the partition 3, 2, 2 is given in the diagram. You can see that it weakly increases along the rows and strictly increases along the columns. So we'll denote the set of all semi-standard Young tableau on lambda with entries in the interval 1k by SSYT lambda of the interval k. So for a box B at position ij, and this is one index, it's like a matrix, I is the row and j is the column. The content of the box B is C of B, which is j minus I. So this definition allows us to define the factorial Schur polynomials. They correspond to a partition and a number of variables k greater than 0. The factorial Schur polynomial s lambda of x1 through xk and z is defined by this formula on the slide. It's the sum over all semi-standard Young tableau on the Young diagram of lambda with entries in k, and a product over all boxes in the Young diagram of x t of b minus z t of b plus c of b. So some special factorial Schur polynomials are the factorial elementary symmetric polynomial, which I mentioned earlier. So this corresponds to a partition that is a single column. And the factorial complete symmetric polynomial corresponds to a partition that is a single row. So here is my Pieri formula for multiplying by a factorial complete symmetric polynomial. So we let hpk of x and z be the factorial complete symmetric polynomial of degree p in k variables, and we let u be an element of S infinity. Then su of x and y times hpk of x and z is given by this formula. It's a sum over certain w related to u by this relation fat arrow k, and the coefficient of sw of x and y is itself a factorial complete symmetric polynomial, but the degree decreases as the length of w increases, and the number of variables increases as the length of w increases. And we substitute this set qk uw for the indices of the y variables, and we leave the z variables alone. So qk of uw is defined as the set of all wi such that I is less than or equal to k, all of those, and union the set of all wi such that I is greater than k and ui is not equal to wi. So if you're interested, the relation is the same as that defined by Sottile for his Pieri formula for ordinary complete symmetric polynomials. So I give an example here. We let u be the permutation 3, 1, 4, 5, 2, p equals 3, k equals 4, and we just take this product, su of xy times h3, 4 of x and z. And I've expanded this product and circled the elements of qk uw, and you can see that those are the indices of the y variables. So I mentioned that the coefficients, when y and z are the same, are gram-positive. This Pieri formula is not directly gram-positive by substitution. However, it's a fact that any substitution of distinct indices of y variables into a double Schubert polynomial is gram-positive by an argument with skew-divided difference operators coupled with a formula of Sarabili from 1999. So you can obtain positivity from this formula because of the substitution of that sort. So now let's get to the hook shape factorial Schur polynomial. So we define a pqk of x and z to be the factorial Schur polynomial corresponding to a partition of the form p 1 to the q minus 1. So this is a hook. It has an arm length. Well, I guess you would usually say the arm length is p minus 1, but there are p boxes in the first row, and the leg length is q minus 1, and this has degree p plus q minus 1. So I give an example here, a222 of x and z. So that is a hook with 3 boxes in 2 variables. So the polynomial is shown, and it corresponds to the 2 tableau on the slide with the given entries. So notice the entries are in the interval 1, 2. So in order to explain the hook shape rule, we need to go into a bit more detail of the Pieri relation. So the Pieri relation u fat arrow k can be defined there existing a sequence of transpositions Ta1b1 through Tapbp for some p, such that ai is less than or equal to k, which is less than bi for all I, and we're going to multiply on the right by these transpositions in order. So we define ui to be u times Ta1b1 through Taibi. So in order for the Pieri relation to hold, the length of ui has to be the length of u plus I. Up, which is the last u, has to be equal to w. And we have this relation uiai is less than ui plus 1, ai plus 1. So this is for the factorial complete symmetric polynomial formula, but for the elementary symmetric polynomial Pieri relation, the condition is reversed. We need uiai is greater than ui plus 1, ai plus 1 for all I. So Sottile did this in his paper. To do hook shapes, we need to mix these two conditions. So the relation depends on more variables here. So we define the hook shape Pieri relation. We let u and w and s infinity be permutations, and we let r and k be integers, r greater than or equal to 1 and less than or equal to k. So then we have this path p, u0 through um, and we say it's in path kr of uw. There exist such transpositions Ta1b1 through Tambm such that these conditions are satisfied. So ai is less than or equal to k is less than bi for all I. And then we have the elementary symmetric polynomial Pieri relation up to index r, not including. And then we have the factorial complete symmetric polynomial Pieri relation from r to m. So, and also the length of ui is the length of u plus I for all I between 1 and m. u0 equals u and um equals w. So given this definition, we can define the hook shape multiplication formula. So su of xy times apqk of x and z is equal to, so we have the first term, which is that of su of x and y, and that's apqk of y sub uk of z, so we're just permuting the indices. This is true for multiplying by any factorial Schur polynomial, or factorial, or any polynomial really. The term of the bottom polynomial is just a permutation of the polynomial itself. And then we have the sum over p in path kr of uw, and we need r to be between 1 and q inclusive, and the coefficient we write as bp of yz. The definition is a bit complicated. It's a product of a factorial elementary symmetric polynomial of degree q minus r in k minus r variables in certain y variables, y sub pk of ur. So that's defined as the number of, well, not the number, the set of all ui such that I is less than or equal to k, and ui is equal to ur of I. So that's sort of the opposite of the complete symmetric polynomial definition of qk. So then we also take the product with h p minus 1 minus m plus r, k plus 1 plus m minus r of y sub qk of ur minus 1. Notice it's ur minus 1 and not ur, and w of z. So this is the formula for the hook shape relation, and it specializes to Sottile's formula if we set y and z to 0. And it can again be made gram-positive, similarly to the other formulas, but not by substitution. So we can generalize the Pieri formula for factorial complete symmetric polynomials to arbitrary alphabets of x variables. We'll let a be a set of positive integers, any set of positive integers, and let u and w be in s infinity. then we define this arrow relation, U arrow A of W, if there exist transpositions similarly to the other Pieri relation, such that the condition now is that AI is in A for all I, and BI is not in A. So this specializes if A is an initial interval to the original Pieri relation, and the conditions are the same otherwise. BI is not equal to BJ if I is not equal to J. The length increases by 1 for each multiplication on the right by a transposition, and W is equal to the last permutation. And then we also define a sign corresponding to U and W, which is the number of I such that BI is less than AI. So these are transpositions that wouldn't occur in the ordinary Pieri formula, but we get signs because A is an arbitrary set of variables, or of indices of variables. So the formula is nearly identical. So we have now the sign -1 to the sigma UW, and it's the same factorial complete symmetric polynomial, but we substitute QA of UW for the indices of the Y variables. And this is very similar. It's the set of all Wi such that I is in A, and all Wi such that I is not in A, and Ui is not equal to Wi. So this is a formula for multiplying by a factorial complete symmetric polynomial in an arbitrary alphabet of X variables. So this is useful in multiplying arbitrary double Schubert polynomials together in the Molev-Sagan case. So to do this, we can use the general alphabet Pieri formula to obtain expressions for double Schubert polynomials in terms of factorial elementary symmetric polynomials. So there's a formula shown on the slide. We have SV inverse of x and z is equal to partial v mu, s mu of x and z. We can expand this double Schubert polynomial corresponding to a dominant permutation in terms of factorial complete symmetric polynomials in one x variable. And then we apply the Leibniz formula and the Pieri formula to get an expression. And then when we flip z and x, this gives us an expression for SV of x and z in terms of factorial elementary symmetric polynomials with various substituted z variables. Then we apply the Pieri formula in my original paper to multiply. And this is actually very fast. So if you install Python 3.9 plus and you run pip install schubmult to install my Python package for multiplying Schubert polynomials and double Schubert polynomials using this method, you obtain 3 scripts: schubmult_py, schubmult_double, and schubmult_yz. So here's an example of schubmult_py. You pass it 2 permutations as shown, and it gives you the product. It expands it in terms of ordinary Schubert polynomials and shows the coefficients on the left. If you want to multiply double Schubert polynomials in the same set of variables, you use schubmult_double. So I show the same product there, and it shows the coefficients on the right because it's easier and better looking to format it that way, and it expresses it positively in terms of yi plus 1 minus yi, which I write as ri. So then schubmult_yz multiplies double Schubert polynomials in different sets of coefficient variables. And here I show the same product. It has many more terms, so I cut it off. And it has an option minus minus display minus positive, which expresses the result positively, which is it does not do by default because it's very slow. So thank you for watching, and you can subscribe to my channel, Maths Schubert Calculus, to see more.